Hello. So today's little lesson is all about solution composition. How do we calculate the strength of solutions? So there's a little bit of math involved in today's lesson, so make sure that you get a calculator. You may also want to have a periodic table. There's just a couple sample problems here. But this is going to be a little short video. This one's part 1 of 2. This one's just going to go through some of the basic composition types of problems, pretty simple stuff. The second part of the 15.2b is actually going to go through some of the applications of this. So moving right along. Why do we even care? Why is this something that we have to do math about? Why do we care how much concentration of a solution is? Well, because really in chemistry, for the most part, we care about how fast a reaction occurs or how much of a reaction occurs. Even as a biologist, most of the chemistry that occurs inside your body happens in solution. And the concentration of those solutions is really critical to how fast a reaction can occur, whether it occurs fast enough for you to survive or perhaps too fast for you to survive. This little picture here is actually a really good example of that. This is the reaction between sulfuric acid and sugar. It turns out sulfuric acid, when it reacts with sugar, produces a little bit of heat. And if you take a look at the two sets of beakers, the beaker on the left in each picture has concentrated acid. The beaker on the right has dilute acid. Each one of them has the same amount of sugar, same amount of water, but a different amount of that sulfuric acid that's in there. And so the beaker on the left, you can see, obviously has a very different reaction to it. Beaker on the right produces a little bit of heat. It's fairly dilute. There's not a lot of that sulfuric acid there to do a lot of heat, so it just gets kind of warm to the touch. But that one on the left gets so hot that literally it starts to burn the sugar, and you get this giant black nasty worm creature. I've done this reaction before. It stinks. You know how bad my aquarium smelled when all the fish died? Well, this is worse. So I don't really want to do this. But you can imagine that if you're trying to digest, say, sugar in your own body, you need to know how much of sulfuric acid, or in your case, hydrochloric acid, you have, so you don't accidentally burn it too fast. So in terms of calculating solution concentration, there's two different ways that we do it. Concentrations always depending on how much solute is present. We generally look at how much of the reactants are there. The background, the solvent, is usually not a reactant. It's usually just there as a medium for the other stuff to kind of float around in. So concentration really focuses on how much solute is present. And there's two main ways that we calculate this. One's called mass percent, one's called molarity, and they're kind of defined down at the bottom. Mass percent is much more commonly used in consumer products, and you'll see the next example I have, it's about like vinegar and lemon juice and things along those lines. Molarity is more commonly used in chemistry applications, and so we'll get back to that concept here in just a second. So let's start off with doing mass percent problems. Mass percent is exactly like it sounds. It is the percent by mass of a solute in a solution. So when you take a look at a bottle of Santa Cruz lemonade, my favorite, in the summertime, it says it's 11% juice. It's not 11% by volume, it's 11% by mass. Your common vinegar, like over on the left, is 5% solution, plus or minus a little bit. And what exactly does that mean? Well, 5% vinegar is mild enough that we can cook with it, but not so bad that it eats through your stomach. So how do we calculate that? Formula's down at the bottom. Pretty straightforward formula. It's a percent just like anything else. You do part divided by whole. So in this case, you've got the mass of the solute is up on the top and the mass of the solution is down on the bottom. So again, be careful with this. The key part here is that this one up here at the top is just the mass of the solute, so it's in grams, and the bottom down here is the mass of the whole solution, not the mass of water, for example. That's a trick question that I could ask you. Mass of the whole solution. Then you multiply by 100, because of course it's a percent, and then you've got your mass percent problem. So here's an example. So if we have acetic acid, and we have 250 grams of acetic acid, say in a beaker or a cup, and we know that it's 5% household vinegar, what's the actual mass of acetic acid that's found? So I'll let you hit pause, see if you can work it out. Remember, the formula for mass percent's up at the top, but see if you can sketch it out. Key point here is when we say mass of acetic acid, is that going to be mass percent, mass of solute, or mass of solution? And when I say 250 grams sample of household vinegar, is that household vinegar, that 250 grams, is that mass percent, mass of solute, mass of solution? All right, hit pause, and we'll go on to the next slide. So here you go. If we take a look at the pieces of our problem that we've got, what's the mass of acetic acid? Well, that's going to be our mass of solute, and that's going to go on the top of our formula. We have a 250 gram sample of vinegar, and that goes on the bottom because that's the mass of our solution. And then the 5% household vinegar, that 5% is our mass percent, so that goes over on the left side right there. So all the rest of this down here is just algebra, so I took that 5 and divided by 100, moved the 100 over to the other side. I multiplied it by 250, again, move that over to the other side. It's algebra. If you're not sure how that works, maybe we should talk after class. And you get a final answer of 12.5 grams is the mass of acetic acid. Again, this step in here is just algebraically rearranging the formula that's up above. So if you need clarification on that, let me know. Okay, molarity. Molarity is a different topic here. Molarity is a different way of calculating solution concentration, and this is what we're going to use almost exclusively here in a chem lab. And the reason why we do this with molarity is because molarity actually takes into account the molar mass. It gives us a better idea of exactly how many molecules are present. Because it doesn't involve grams, it involves moles. So you can take a look. The equation for molarity is up at the top there. It's moles of solute divided by liters of solution. So it's moles per liter, a little bit different units. And it's abbreviated with this kind of, it's an italic M sort of crooked thing. And this, when you see this M like this, it means moles per liter. Moles of solute per liters of solution. So solving these kinds of problems isn't really particularly bad. It's the same kind of stuff that we've done before. You're usually trying, you've got two of the three and you're trying to find the other one. So there may be a little bit extra calculation to do. So let's show you an example problem of what this looks like. So here's an example. What's the molarity of a solution prepared by dissolving 2.80 grams of sodium chloride to make 135 milliliters of solution? So if you take a look at our molarity equation, we're trying to calculate molarity. That's what we're trying to get. We need to know moles of solute, and we need to know liters of solution. So here's our calculation strategy. Number one, we want to calculate the moles of salt. We've got grams. We need to convert grams of salt, sodium chloride, to moles of salt. So we're going to use molar mass for that. Part two, we need to know liters of solution right here. And we're given milliliters of solution. So we have to do a second little conversion to make sure that we're in that. And then we just divide the two. So here's what it looks like worked out. There you go. So here's that first step. Step number one, this is that grams to moles step. The molar mass of sodium chloride is 1 sodium is 23. I think 1 chlorine is 35. So when you add those together, you get 58.45 grams. That's where that number on the bottom came from. Divided out, 0.0479 moles. The bottom one, this is converting from milliliters to liters. Basically, you're just moving the decimal place over 3 places or dividing by 1,000. Either one works, whatever you like. We get 0.135 liters of solution. So when we divide those two together, here's what you get. 0.0479 on the top, divided by 0.135 liters on the bottom, moles per liter, and you get 0.355 molar solution. And that's how you'd actually pronounce that goofy looking thing. So the answer would be 0.355 molar, or molarity, is the solution of this. So in the next video, the next little short one, we're going to kind of take this idea of molarity one step further. Now you know how to calculate molarity. We're going to apply this concept of molarity to a couple of different problems. Number one, we're going to be able to figure out how many types of ions are present in solution based on molarity. And number two, we're going to prepare standard solutions. So that's something like, I need a 2 molar solution of something. How do I prepare that? So there you go. See you in class. Actually, I'll probably see you after the next video.